Okay, let's get into some details. First, we'll focus on verifiable system requirements. Here, I want to first make the point about the value of specifying requirements in the context of an architectural design model. And the reason is the following. Here is an example of a set of textual requirement specification that seem to look quite reasonable. They are from a University of Minnesota study from Mike Whalen, actually, and everything looks reasonable. But when you go into the detail of what they refer to when they use the word system, what we find out is that we actually are dealing with 4 different requirements, each addressing a system or subsystem at different levels within the system hierarchy. The main point is, when you write requirements, you tend to have in mind already a partial architecture by specifying these requirements and identifying in the context of a model which piece of the system you're talking about. You realize how much of an architectural specification you already have partially either assumed or are passing on to the person developing the system. The second piece of it is it helps you understand what the system boundary is of the system do you expect somebody else to design, and how much are you fiddling with specifying the internals of that system to the person producing the system. So with the notation, the objective is a RegSpec is a textual notation that was trying to cover the space of what was defined in a draft annex proposal for what's called at that point the requirement definition and the analysis language. It was a meta model specification by some people in Europe that drew on goal-oriented requirement specification. So a lot of that, all of that got reflected in this notation. The meta model also built on this notion of uncertain requirement uncertainty. So we have those kinds of things reflected as well. So the objective is support goal-oriented requirement specification, have linkage between stakeholder goals and requirements, support requirement decomposition and refinement as well as evolution in specific terms, not just as requirements and derived requirements, integration with safety analysis, how do we reflect exceptional conditions and have requirements that then address these exceptional conditions. And it becomes really the primary focus from our end is that it becomes the basis for driving this automated verification. On the stakeholder side, the ARDAL, whenever they did all that, did a whole bunch of work, including an integration with use case modeling, such as using UML and SysML type of use case notations, or the ITU UCM. And there is a Java-based implementation of that one can tie into that. At this moment, we have not integrated that particular thing as part of the front end because our focus has been on the back part of it, the verification of the system. And so this is what the system requirement specification part is about: a consistent set of system requirements that must be met by a delivered system. And the way we show that they can be met is by doing continuous verification through assurance plans. So it becomes a verifiable contract recorded in verification, expressed through verification plans. It's associated with an ADL classifier or an element within a classifier. So what I mean with that is, if I have a device type, I have a set of requirements for the device as a whole, or I can specify some assumptions on input on a device, or some requirements about the output of a device, or requirements about resources it uses, whether it's physical power or interface with the computer. There's some basic notational things like fields for description and rationale, but more interesting from a verification perspective is the ability to parameterize the requirement so that a parameter can then be used not only in the requirement but as parameter to the verification activity as well. I already mentioned refinement, decomposition kind of things, and inheritance. And the ability of a specification of a predicate that then can be automatically executed, and the usual traceability type of things. Requirements are grouped into what we call requirement sets. So you can specify a set of requirements for a particular component type or component implementation. So the requirement set identifies the classifier, and then you list individual requirements that either apply to the component itself or to particular elements, whether it's a as I mentioned, a port, or whether it's a connection, or whether it's a end-to-end flow. We can have inherited requirements because we have classifiers that can be extended into other classifiers. So I can have a device type and an extension to the device type. If I now have requirements attached to the original device type and now define an extension, the original requirements are inherited, and you can add new requirements to the extension itself, and it's the combination of those requirements that are supported. In addition, we can have global requirements that can be included specifically to individual components or configured in at the assurance case level, and those are organized in global requirement sets. Individual requirements are illustrated here. So I have a requirement set for a particular system called simple control system. And by the way, the simple control system is an example that is available on the ELISA website. Let me just switch for a moment to that. So here is the OSATIC GitHub site. Under ELISA examples, we find a simple control system and some description further down on how to install the simple control system. Basically, you need to install ELISA predefined and cyber physical, and then the 3 projects under the ELISA example simple control system. This is also the system that I will be using to show the actual running system. Okay, back to this view here. So we have a set of requirements for SCS, which is a system type. I can have some constants defined here, like maximum latency, and then I kind of have a collection of requirements. Each requirement has a name, some textual label for display purposes, be more descriptive. You can have those constants defined locally to a single requirement or for the whole requirement set. We have category marking, and I'll elaborate on that later. You can then have predicates specified. In this particular case, we indicate that the value specified up here must be the same as the value recorded in a property within the model. The idea of these variables is that we can make use of them in, for example, in the textual description, so that and secondly, we can refer to them in verification plans. So here, for example, we are referring to maximum weight as a value to be passed to a verification activity. The idea behind that is again, we have found in practice, and Rolls-Royce and others have confirmed that when you look at requirements, in many cases the change tends to be in particular values that are specified as part of the requirement. So first of all, you might want to specify that as a range of values, but the other part of it is when you change the value, we now change it just in one place, and it automatically gets propagated in all the different areas that result in generated documents, or in this case also verification plans. One of the things that we run into when we do requirement specification, and you have already used AADL, you tend to have reflected certain requirements as properties. Like, for example, what's the weight limit, or what's the power budget, or what's the expected end-to-end latency. So you could have those. Now, when you have models like that already in place, one way of defining requirements is that in the requirement specification itself, like on the previous page, instead of using constants, I refer to the property in the model. So that's my first scenario. So in that case, the parameters to the requirement are already in the model itself and not in the val thing. So that is a situation that you may want to use when you have already existing models. The second scenario is, well, we specified the val variable on the requirement side, and we get Alisa to make sure that those values are set as properties in the model, because an analysis assumes that the values are there as property rather than passed in as parameter. So we have a way of doing that by specifying a verification method in which the parameter passing is to be done. We'll see that in a moment. The third scenario is where you do have the values in the requirement and as a property already in there. In that case, we want to establish that the two of them are consistent. And that can be done by either you writing an explicit value predicate into the requirement, or by, when specifying the verification method, the consistency of the value is checked as part of the method invocation that depends on certain properties. One of the things that you're facing when you're doing requirements, there is requirement decomposition. As I mentioned earlier, people often talk about derived requirements. We distinguish between requirement refinement. A requirement refinement means I have a requirement for a system that says the system shall be safe, and you refine it into requirement for the same system, a set of requirements that are more concrete, that become verifiable. That's called a derived requirement. Requirement decomposition is different in the sense that a requirement on a system implies requirements on various subsystems. And so we have support for that as well, so you can actually identify how requirements on a subsystem relate to requirements in a contextual system. The second piece of it is then doing verification plans, and for that, before we do that, I wanted to switch and show you some examples of requirements in OSATE setting. So here we have OSATE, and we have downloaded through GitHub, which you can do by switching over to the GitHub view and registering Alisa examples as a remote GitHub site. And once you have that site, like we were showing on the website before, I want Alisa predefined, cyber-physical, and the three subsystems, the three projects that are Alisa consistency, JUnit test, and simple control system. What you would do is just once you have that import those into your workspace. So when we switch back to our workspace, Alisa predefined basically just has a plugin method registry and a predefined set of categories. Cyber-physical provides some properties and some resource definitions as abstract types, so you can talk about notions of electricity and other things. Some examples are like voltage is the primary example we have in there right now. And the most interesting part is the simple control system. simple control system. There's the ADL model. It's just a basic control system that has a digital control with a hardware platform and some software on it, and it's getting data from sensors and activates actuators. So if we open the model, the top level system has some external power source, and as a control system applies physical force through the actuator to some external entity. And the physical system is organized in 2 sensors and 1 actuator, and then the digital control system. And that then gets elaborated. Digital control system is then again the software application. That's the software part of the control system, and the platform. And then we configure the platform in different ways with single processor, multiprocessor. At this level, we already have flow paths, so there is an end-to-end flow at the top level system implementation that we can, for example, verify. That here's the end-to-end flow for the system, and some properties about latency and other things. Okay, so that's the ADL model. And then we have, there's a diagrammatic view of the whole thing too, so you can see those in the graphical editor as well. And that's the built-in graphical editor that we have. So here is the 2 sensors going to the digital control system to the actuator. And we have 1 flow. You can highlight the flow by selecting the flow up here for visualization. So in terms of the ELISA part, what we have is a set of requirements for the top level system as well as each of the subsystems. And let's open the RegSpec file, which is the one for the top level system. And that's the one we saw on the slide. So that's the one that deals with weight and other things, and voltage type of characteristics. For the end-to-end flow, that doesn't exist at the spec level. So for that, we have to have a requirement on the implementation, the tier 1 implementation of the SCS. And that's where you then find our latency requirement up here. Okay, and it is for the tier 1 specification. So here's the latency, and when you look at the requirement specification of the latency, this is where we indicate this requirement doesn't apply to the component as a whole, but it identifies a particular feature. In this particular case, it identifies the end-to-end flow. Okay, and then there's some other requirements in there. These are now decomposable requirements, that is the top level requirement. R1 that we had here about weight limit decomposes into requirements of certain subsystems. So this becomes a requirement on DCS, and then the next one becomes a requirement on sensor 1 and a requirement on sensor 2. And we can then compare those against the requirements that are associated with the sensor itself. Okay, let's put the